So this is joint work with my two graduate students, Safar and Yang, who are both here, and Gregory. Okay, so I'm going to talk about matching in streaming model, and just a very quick reminder of the matching problem. So matching in a graph is a set of edges with the property that every vertex has at most one edge incident on it. So in this graph, the red edges form a matching. And the maximum matching problem is simply to find largest matching in a given graph. Okay? The special case of matching where every vertex in the graph has an edge incident on it in the matching is referred to as a perfect matching. So the red edges here actually form a perfect matching. The streaming model has been defined multiple times today, so I won't go over it again. And so the focus of this talk is going to be designing algorithms for solving the maximum matching problem approximately in the streaming model. And there are basically two main variations which one can consider here. So the first model is the simpler model where the graph is going to be revealed to you one edge at a time, and the edges are only being inserted. So we refer to this as the insertion-only stream. And the second model is where the edges of the graph are also revealed one at a time, but I am allowed to delete edges. So I can insert edges and delete edges, and each time I tell you at each step an edge which is going to be inserted or deleted in the graph. Okay? And throughout this talk, I am just going to focus on single pass stream. That means the algorithm will get to see the data just once. Okay, so what do we know? So we have known for quite some time that exact computation requires omega n square space even in the insertion-only streams. Okay? So if you wanted the exact answer, you cannot do anything meaningful in terms of saving space. On the other hand, if you are happy with the two approximation, then order n space is enough. And this is a very simple algorithm. You can simply maintain a maximal matching. It's a greedy algorithm. Each time you see an edge UV, if it isn't already part of your matching, U and V are both free, then you just add this edge to your matching. And a maximal matching is a two approximation, so this is a simple two approximation algorithm. And here the main question has been to beat this factor 2 by using n polylog n space. And at the moment, the only interesting progress in this direction is if you assume that the edges are being revealed to you in a random order, then you can get some small improvement over the factor of 2. It's a very small improvement, and this already requires a fair bit of work to get. And we are also aware of a barrier here, which is there is an absolute constant e over e minus 1. If you wanted to get an approximation here which is better than this factor, then you need superlinear in n space. Okay? Good. For the dynamic graph stream model, where the edges are both inserted and deleted, to my knowledge, until recently, there were no non-trivial results known for single-pass algorithms in this model. And this is the setting that we are going to focus on. Okay, so before I describe our results, one more tool I want to quickly describe, which is the idea of using linear sketches. It's a tool which is widely used in designing streaming algorithms. And a linear sketch of a data is simply a random linear projection of this to some smaller number of dimensions. So in context of our graph problem, you can think of the graph as being an n square dimensional vector where there is a coordinate for every possible edge slot, and the vector describes how many times the edge appears. So it may be simply a 0, 1 vector, which just tells which edges are present, which are missing. And if you take a R by n square matrix A and multiply this matrix A with the vector f of the edge multiplicities, you get an R-dimensional vector, which is a linear sketch for my n square dimensional data. Okay? And the space now is reduced from order n squared to order r once you do this transformation. And linear sketches are very handy in streaming algorithms because now each time you do an insertion or deletion of an edge, I can update this sketch on the fly. I simply compute I look at the edge which is being inserted or deleted. I look at the incidence vector for this edge, and I simply apply the matrix A to this and update my sketch. Okay. So the space requirement for such a streaming algorithm is going to be simply order r if the matrix A was r by n squared, plus what you need to be able to create or implicitly store the matrix A. Okay? So if you're using some amount of random bits to generate this, so you presumably would need space for that. Okay? And at the end of the stream, the algorithm looks at this linear sketch and does some computation to recover the answer. Okay? Pretty much all known existing dynamic graph streaming algorithms are linear sketching algorithms. So this is essentially the main technique that we have for designing algorithms for dynamic graph streaming problems. Okay, so now I can tell you about what are our results. So this talk is about understanding what you can do using linear sketching in terms of approximating matchings in dynamic graph streams. And the first result is a positive result, which says that essentially for any epsilon less than half, if you wanted a n to the epsilon approximation to the matching problem, then you can do so using roughly n to the 2 minus 3 epsilon space. Okay? So if you settle for n to the epsilon approximation, the saving is cubic in the approximation factor over the trivial space requirement. Okay? And moreover, the algorithm is efficient in terms of the update times. It just takes polylog n time per insertion or deletion. We have a complementary lower bound result also, which says that this is essentially the best possible thing you could do if you're looking at linear sketching algorithms. And specifically, it is saying that if you wanted to use a linear sketch to recover an n to the epsilon approximate matching, then you do need n to the 2 minus 3 epsilon space. Okay? So in some sense, this is resolving what you could do using linear sketches for this particular problem.
Excuse me.
Yeah.
This is in the exponent little of 1 or?
Small o of 1. Yeah, big O of 1 would be very problematic. Yeah, thank you for pointing that out. Yeah. Okay. So until recently, not much was known, and then suddenly, I think several groups simultaneously made progress on this particular problem. So independently and concurrently of our work, there are two other sets of results of similar flavor. So the first one is by Conrad, who looked at the same problem and showed on the upper bound front that if you want to get n to the epsilon approximation, then n to the 2 minus 2 epsilon space suffices. So this is somewhat weaker than the bound that we obtained. And Conrad also shows a lower bound, which is n to the 3/2 minus 4 epsilon, also weaker, but the result is in the similar flavor as to what we are showing here. And then there is the work of Chitnis et al. Actually, several of the co-authors are here. Andrew and Graham are here.
And the rest open.
Oh, okay, and Vorotnitsvoa is also here. Okay. And this result is exactly the same as our upper bound result. Namely, you can, for epsilon less than half, you can get n to the epsilon approximation in n to the 2 minus 3 epsilon space. Okay? And the ideas are also, in fact, similar. Okay, okay, good. So in the remaining time, I'm going to tell you a bit about both these results. Both results are based on simple ideas, and should be able to tell you a bit about both of them. Definitely about the positive result in fair amount of detail. So I'll start with the positive result, which is just showing you can get n to the epsilon approximation in n to the 2 minus 3 epsilon space. Okay. And as I said, the algorithm is going to maintain a linear sketch. And we're going to assume, without loss of generality, that we are working with bipartite graphs. If you're willing to lose a factor of 2, it's easy to do a reduction of your problem on any graph to a bipartite setting. So I'm going to assume we are working with a bipartite graph G with the left vertices L, right vertices R, and an edge set E. Also, just to keep the presentation here clean, we're going to assume that the graph is a perfect matching. We don't need this assumption for our theorems to hold, but it will just make the presentation much easier. So M star is this perfect matching in the graph. And we're going to rely on a tool which is widely used in streaming literature, which is the L0 sampler. And what this tool does is it solves the following problem. So you're being given a stream of insertion and deletion of elements over some universe of elements. And the tool allows you to output uniformly at random among all elements whose L0 norm in the stream is non-zero. Okay? So you look at the elements being inserted and deleted, look at the L0 norms of their multiplicities. Among the elements which have non-zero multiplicities, it will output one of them uniformly at random. And it turns out it's possible to implement such a sampler in a very small amount of space, actually surprisingly small amount of space. If you want constant probability of success, then you could implement such a sampler using only order log square n space. Okay? So that's a tool that we are going to use in designing our algorithms. And the high level, the plan is use L0 samplers to maintain some subsample of edges in the graph, carefully chosen, so that we will be able to argue that in the end we have a large matching in this subsample. Okay. So let me start with a very simple algorithm, which is going to give us n to the epsilon approximation in n to the 2 minus 2 epsilon space. And then I'll show you, by adding one more idea to this very simple algorithm, you can actually improve the result to n to the 2 minus 3 epsilon space. Okay? So here is the idea. On the left is my original graph, where the left set of vertices is L, right set of vertices is R. And what I'm going to do is I'm going to randomly partition vertices on each of the two sides into groups of size n to the epsilon. So now I have a new graph G prime, which consists of n to the 1 minus epsilon groups on each side. And I'm going to contract these groups and start to view it from here on as singleton vertices. Okay? Now, once you do that, your original graph G with a perfect matching M star now corresponds to a new graph, which is an n to the epsilon regular graph, and has only n to the 1 minus epsilon vertices on each side. Okay? And there is a standard fact that if you have a deregular bipartite graph, then it contains a perfect matching. So this n to the epsilon regular graph is going to contain a perfect matching. And if somehow I could store all the edges which are present in this n to the epsilon regular graph, I would be in good shape. Okay? And that's exactly what we'll do. We are going to, for every possible slot, we are going to maintain an L0 sampler, which is going to track as edges are being inserted and deleted for that pair of groups. It's going to track this these insertions and deletions, and in the end output an random element. We don't need it to be random. An arbitrary element would be just fine. And we are going to pay order log square n space for each of these slots. So this immediately gives you n to the 2 minus 2 epsilon space algorithm now. Okay? Good. So let's improve it with one more observation. And the observation is that what we did here, where when we maintained all possible edges among these groups, it's an overkill. We don't need so much information to recover a large matching. And in particular, you can do the following thought experiment. If I gave you a deregular graph, and you randomly sampled every vertex on the left, randomly samples one of the D neighbors on right, uniformly at random, then the resulting set of edges is going to contain a matching of size omega n. Okay? It's an easy calculation to show that. Okay? And that's the intuition we are going to implement here. So instead of me trying to track for every group on the left all its set of edges, all I want is to get one uniformly at random neighbor on the right. Okay? And for that, it is enough for me to maintain an L0 sampler to n to the 1 minus 2 epsilon groups. Why? If you look at this group Li, it had n to the epsilon edges going out in the M star. Those edges, because of my random grouping, are going to be well distributed on the other side. So there are n to the epsilon groups on the right side, which are receiving endpoints of these edges. Out of n to the 1 minus epsilon groups, n to the epsilon groups are good for me. So if I sample n to the 1 minus 2 epsilon such groups at random, I'm going to, with constant probability, hit one of those groups. And that's it. That's exactly what we do. Okay? And this shaves off now the space from n to the 2 minus 2 epsilon. It improves it to n to the 2 minus 3 epsilon. I assume throughout here that you have a perfect matching, but exactly the same algorithm with the different group sizes based on the matching size works with the same algorithmic idea. Okay. How much time do I have?
12:45 is the cutoff.
Okay, but we started. Okay, all right. So just a quick summary of what the algorithm did then. We started with the original graph here. We randomly grouped vertices into groups of size n to the epsilon. And then for each group on the left, we chose n to the 1 minus 2 epsilon groups at random on the right, and we maintain L0 samplers for all these pairs. That's the entire algorithm. Okay? Good. So in the remaining time, I can try to tell you a little bit also about how we get a matching lower bound. So I want to show you that if you want to get an n to the epsilon approximate matching, then you need n to the 2 minus 3 epsilon space if you're using linear sketches. So we're going to prove this indirectly. We're going to go through by looking at the simultaneous communication complexity of the matching problem. So the setting for the simultaneous communication complexity would be the following. The input graph I'm going to assume is going to be partitioned among k players. And the task that these players have is to send information about the piece that they hold to a coordinator. And the coordinator needs to collect enough information to be able to recover an n to the epsilon approximate matching. And the quantity of interest here is the maximum number of bits that any one of these k players needs to send to accomplish this. It's a folklore thing, and it's an easy thing to show that if you can show a lower bound on the communication needed in this model, that translates into an identical space lower bound for linear sketching algorithms. Okay? And the proof is very simple. It's basically if you had a linear sketching algorithm, then each of these players could be running that linear sketching algorithm, and the coordinator can simply compose together these sketches. Okay? So let me tell you a bit about how the lower bound comes about. Okay, good. So we are going to use a special class of graphs to establish this lower bound. And this class of graphs is called the Ruza-Zameradi graphs. And they have a very interesting structure. These are graphs where the edge set can be partitioned into a large number of induced matchings, each of which are going to have large size. So for example, an RT-RS graph would be a graph where the edge set of the graph can be partitioned into T induced matching, each of which have size R. Let's do an example. So this is the 2, 4 RS graphs on 8 vertices. So each matching, 2 is the first parameter is the size of the matching. So each matching will have 2 edges. And the matching is induced. So it means if you look at the vertices that define the matching, there are no other edges present between those vertices. Here is another matching I can pack. Here is another matching. And this is the last matching that I can pack here. Now, if you think about it, if I told you these matchings, if I have an n by n bipartite graph and I told you these matchings are almost omega n size, how many edges do you think such a graph can have? So each time I show you a matching of size omega n, I also rule out omega n square edges from existence because the matching needs to be an induced matching in the graph. I don't know what is your intuition. My intuition when I first came across these graphs was it can't be dense. But the surprising fact is that even when the matchings are almost the size of the total number of vertices, each matching is an induced matching of size close to the total number of vertices, the graph can be almost quadratic dense. Okay? This is a non-trivial fact, that you have such graphs where the edge set can be partitioned into matchings which are almost as large, induced matchings which are almost as large as the total number of vertices, and yet you can pack omega n of them. Okay? And we are going to use these graphs to construct our lower bounds. So let's look at what is the view of each player, what is the input for each player. Each player is going to get an RS graph with the parameters shown up there, where for every matching, induced matching, I'm going to drop half the edges at random in the RS graph. Okay? And the parameter n, capital N here, you should think about is roughly small n to the 1 minus epsilon. Okay? So these graphs are going to contain about n to the 2 minus 2 epsilon edges each. Now, one of the induced matchings among omega n induced matchings, one of them, the one with red edges here, is going to be a special matching unknown to the player. Okay? That's what the adversary will choose. This is as a special matching. But the player's local view, all of the omega n matchings look exactly the same. Across the players, vertices in these special matchings are all going to be unique. But those yellow vertices, the rest of the vertex set, is all going to be shared. So everyone gets the same set of shared vertices and something which is unique, but they have no idea which vertices or which particular matching is defined to be the unique matching for them. Okay, so here is how the picture looks. So 2 players, and they have the yellow vertices are common to them. Their local views consist of the yellow vertices and the green vertices, which define the special matchings. And when you superimpose, the yellow vertices were the same in the 2 inputs. The graph looks like same set of yellow vertices and then repeated set of these green vertices. Okay? So you can see if I continue this process for k players, the optimum matching size would be almost everything, because those green things, they are all distinct. So optimal matching will be almost a perfect matching. Okay? And now we could show just two simple claims that if the set of the information that you have sent to the coordinator allows you to recover only about n to the 1 minus epsilon red edges over all the players, then the matching you are going to get is going to be smaller than the optimal matching by a factor of n to the epsilon. And the second observation is, but if each player sends less than n to the 2 minus 3 epsilon information, then there is no way to be able to send any meaningful amount of information about the red edges. Because to each player, the red edges are same as any other matching edges. So whatever information you send is essentially uniformly distributed across these matchings. Okay? That's it. That's basically the idea. Okay? So let me just wrap up here. So what I showed in the talk was for epsilon less than half, n to the 2 minus 3 epsilon space suffices for any linear sketching algorithm, and it's also necessary. So it's tight in this regime. And actually, for the you could ask the question, what happens when epsilon is greater than half? There also you can use the same ideas to get a tight answer. The lower bound turns out to be trivial actually in that setting. And you can show that when epsilon is between half and 1, n to the 1 minus epsilon is the right answer. Okay? You need n to the 1 minus epsilon space just to write down the matching. And that turns out to be also enough to recover such a matching. I focused on saying that we are resolving what can be done using linear sketching algorithms for the matching problem. But there is recent work, and in particular the work of Aihu and Woodruff, which is very, very recent, which basically shows that if you can show lower bounds for these linear sketching algorithms using simultaneous communication complexity, then in fact they also translate as lower bounds on what you can do for any dynamic graph streaming algorithm for the problem. So this qualification of linear sketching is without loss of generality. Okay? So we started with linear sketching, but thanks to these results, we can actually conclude this is the best you could do using any algorithm. And I want to conclude with one of my favorite open problems in this area, which is going back to insertion-only streams. And I said that if you just maintain greedily the maximal matching, then in order n space, you can get a 2 approximation. We don't know, even if you're willing to go much beyond order n space, let's say n to the 3/2 space. At least I'm not aware of any algorithm for actually n to the 2 minus epsilon space which beats this factor 2. Okay? And we know there is a barrier at e over e minus 1, which seems to be the kind of a dangerous territory because we don't know how dense RS graphs can get in that regime. But between 2 and e over e minus 1, there's no evidence that such an algorithm cannot be designed. And it's a tantalizingly simple problem to state, but seems pretty hard to make progress on. That's all I wanted to say. I'll be happy to take any questions. Yeah?
What's your conjecture for this tantalizing question?
I keep oscillating. I've tried very hard to think about on the algorithmic side. And, but now I start to feel maybe it was just blind faith. I thought the progress has to be on the algorithmic side. So I do not know. And,
the lower bounds do not apply if you only care about the value of the max.
yes, no, they do not apply. Yes.
Is anything known about that?
We think we can adapt some of these things to recover something weak, like of the spirit of maybe n to the 1 minus 2 epsilon or something like that. But it's off. It's below n, way below n. And But on the positive side, we do not know. Okay. We know something about the insertion-only streams. You can get a polylog approximation in polylog n space, but not for the dynamic stream. Oh, okay, yes. Yeah.
There is no sign for constant epsilon, or does it convey, for example, like epsilon equal log n over log n, just to get something?
Let me, so you're talking what happens if epsilon is below, like something which is decreasing. I think it should carry on for a regime which is where the epsilon is diminishing, but I would have to think about how far down you could push. Okay. There will be some place where probably it will break. Yeah.
All right, thanks.
Okay, thank you.